Let me take my Robocop additions out. So we describe, so yesterday we end up in that little cartoon, right? This is the good moment, by the way, when you're in the cartoon time. You make cartoons, and those paper detectors are all characterized because they are perfect. They work really nicely, right? Um, the problem is that you need to later build them. And so let me show you step by step how you pass from paper to reality. So the first thing I described, remember, was the lead castle that shields the whole detector from the external wall. And here you get the castle itself. What you can see here is all this more than 30 centimeters is lead. And so the lead is surrounding completely the detector that is inside. Now, to give you an example of things that can go wrong easily in a neutrino-less double beta decay experiment, this lead that you see in this kind of gray color originally was red. When we made the structure of the lead castle, which is made of steel, the guys who made the structure decided to paint in a very nice red paint, which was shiny and beautiful and protective, but they didn't understand that it was radioactive too. So just the radioactivity that was introduced by the paint, this radioactivity was shielded by the lead. Huge amount of lead shielding the radioactivity from a tiny layer of red paint, and it was not enough. The background was very high. We could control it in next white, but we understood we could not possibly run next 100 with the amount of radioactivity that we would get just for the paint. So we had to dismount the whole lead castle, bring the extractor back to the shop, and remove the paint. Okay? So this is one example of many of things that can go wrong when you're trying to build a low radioactivity experiment. The next thing that you saw in the picture was the pressure vessel. So of course, next is a high pressure xenon experiment. We want to play with pressures that are at least 10 bar. And then you need a pressure vessel. Pressure vessel means you need to make a vessel of steel with thick flanges, with screws and all this. Now the good news is that the steel itself, which you can find pretty clean steel, okay? Meaning that the level of radioactivity of steel can be decent. But remember the exercise that we started to work on yesterday? And remember that I told you that you could use something of the order of microbecquerel, 3 microbecquerel or so per kilogram for ultra pure copper. In the case of steel, the best you will get is 3 millibecquerel per kilogram. So you have 1,000 times more radioactivity coming to your detector from the steel only. So obviously you cannot have a pressure vessel made of steel and then live with that. You need to shield the activity that comes from the steel with something else, with copper. Now, an obvious question is why wouldn't you then build your pressure vessel of copper? Okay? The answer is that it's not possible. No regulation, not in Europe, not in the US, will let you, maybe in China, will let you build a pressure vessel of that characteristics with copper. You can build, as Nexo proposes, a vessel at 1 bar atmosphere if you want. But if you want to take the tensions that are associated to 10, 15, 20 bar, you cannot do copper, okay? So you need to do steel. We have for a long time thought in titanium, which is better, but we have never fully succeeded to find sufficiently radio pure titanium. So steel is fine. And then, of course, as I said, you cannot live with the radioactivity that comes from the steel, so you put copper, all right? And in the case of next 100, there are 12 centimeters of copper, which is enough to kill. Remember that copper is 3 centimeters or so per attenuation length, so it's 4 exponentials that you are putting, right? So this is enough to attenuate the radioactivity that comes from the steel and from elsewhere. And eventually you need to worry about the radioactivity that comes from the last bar or so of copper, which is not self-shielded. And that reduces to the problem that we would be discussing yesterday. All right, so you need to make, remember that we discussed about making the electroluminescence. Recall that next is a light TPC, so you drive your electrons, you arrive to a couple of grids, and you accelerate the electrons, and you produce, per every electron, you produce 1,000 photons, 500 photons, right? Now, you need to build those grids, and those grids are things which are about 1 meter diameter, right? And you have a tiny, tiny honeycomb wire structure. These are difficult things to build, and actually it's one of the issues that we don't know how well they scale. So in next white, the grids were about 0.5 meter, and it was comparatively, well, not very, very, very easy, but not very, very difficult. Stretching this honeycomb grid for 1 meter, it's already at the limit of what any company in the industry will do for you. And stretching the grids for 2 meters doesn't seem to be something completely easy. So we may need to change the technique of the grid stretching from next 100 to the next thing and go to modular. So it's important that you realize that little things that, you know, it's like aligning a drawing when it comes to paper, they become engineering serious issues when it comes to real detectors. Anyway, these are the grids. And then here you can see the TPC. So the TPC has these bars of plastic. And then you start to put rings. And then you connect, you see the rings. So here is the cathode. And then you have the rings, and you will connect the rings with resistors, right? So as you see the pictures, and at the end of the day, you have, this is the tracking plane where we will put the silicons, and you can see these little holes. These little holes are for the cables that come out from the silicons to go out. So if you look at here, you can get a feeling of what kinds of backgrounds we need to deal with. So what you see here all around the place is mostly copper. Okay? So one problem that we have is that our copper, the copper that makes up the shield, the rings, and must be very, very radiopure. Okay? At the same time, there is a lot of copper. So there is a compromise between finding sufficient copper and sufficient radiopure copper. Other things can completely destroy you. Suppose that you get very radiopure copper and then you are all fine. Well, you still need to be careful with this plastic here. There are some plastics that are kind of okay. So we are using here HDPE, high density polymer, which has sufficiently low radioactivity, although difficult to measure, by the way. So you are never completely sure of how much radioactivity you have until you start to operate. But then you need to connect the copper rings with resistors. And these resistors, you need really to put attention on those resistors. If you use normal resistors, you buy them in the shop, you're dead. They are hot like hell. So you need to manufacture themselves. And you need to understand, as Ricardo was explaining this morning, we measure everything that goes in, okay? And then we hope that everything that goes in is well measured and we can add them for our background model, but it's not obvious. Any little mistake can cost you ununderstood sources of background. By the way, if you kind of look at the pictures laterally, you will see that this thing that looks transparent in reality is the grid. We'll see a bit more of a picture here. So now the silicon PMs, these are the silicon PMs which are put into Kapton layers. So the silicon PM themselves are very, very tiny radioactivity to the budget. The Kapton is also pretty clean, but it adds more than the silicon PMs themselves. Now, on the other side, you have the PMTs, but the PMTs need to be decoupled by high pressure resistant sapphire windows. And these things, you can see this kind of glow. They are called, why this thing is glowing in blue, by the way? Because we illuminated it with a VUV light, and there is TPV all over the place on the silicon PMs, on the PMTs, so all the VUV light becomes blue light, okay? So one of the features of NEXT is that it is, all the sensors contain evaporated TPV on top so that we can, by the way, and this is an interesting detail, you could imagine that since TPV works well in the case of NEXT 100, we could also use TPV for liquid xenon, right? Why not? Well, no. Xenon gas does not attack TPV. Instead, liquid xenon dissolves TPV. So when you try to make the same technique from gas to liquid, it doesn't work, okay? All right, here you have the tracking plane. And what are you seeing in the tracking plane? Again, this is Teflon. And why am I putting the whole thing on Teflon? Because we want it to be reflective. We want to recover all the light, okay? Teflon itself is rather clean, but again, we are putting a lot of Teflon here. So how much radioactivity we can tolerate, we will see. Then silicon PMs are on these little holes, and this is the whole tracking plane. You can see by looking at the thing where my pixels are. Very pretty picture. And then this is the TPC being mounted. And once you have the whole thing assembled, you put more Teflon. Why? Because you want to recover all the light. See, now you can see this thing on Teflon and Teflon panels all over the place. Why? Because you need to recover all the light that is inside your detector, okay? So for sure, NEXT works like many other experiments in the Matryoshka thing, right? So you go inside a mountain because you need to defend yourself from the cosmic rays, and the walls of the cavern shoot you things. So you put lead or water, and then the lead shoot you things, or the steel shoot you things, so you put copper, and so on until you arrive to the inner part of the detector. What you cannot shield, it's the sensors themselves, right? So you need to have enough radio purity on your inner components so that you can control them with your techniques of background reduction. So here is the spectrum. I hope that when I get the lectures from Ricardo, I think I want to prepare a very nice plot for other lectures where I want to show Legend, Next, Nexo, and Kamlanzen spectrum, because it's very spectacular. The peaks are very, very thin in the case of Legend, then become a little bit bigger in the case of Next, then they become bigger in the case of liquid xenon, then they become no peaks, but undulations. And it's very interesting because you want to, exactly these peaks are the one, this is the bismuth peak, this is the thorium peak, and where are we? Here, right? So the size of this peak defines your resolution, and your resolution is what you are able to do to separate as the first tool to separate signal from background. So I decided to use that thing, this is from the thesis of one of my students, just to scare the hell out of you, all right? So you start to do the calculations. How much background comes from different things? Okay, the vessel, for instance. So the vessel and blue, interesting is blue is thallium and red is uranium. So in the case of blue, you should be a little bit less scared than in the case of red, because of this. Thorium is here, okay? So, and I am here. So the background that comes from thorium is kind of very, very flat, and it can be also controlled by a number of ways. While bismuth is on top of me. So things in red are scary, things in blue are scary, but not so scary. So you can see that there is a bit of background from the vessel. Remember, the vessel is steel, but it's shielded by the copper. So not that much, and less from uranium. Then quite a bit coming from the silicon PMs, not the silicon PMs themselves, but the Kapton boards. Then the Sapphire windows, Safari windows in our lingo. Again, a lot of thorium. Okay, all this is the rate that will come into my detector if I would do nothing. I just put the detector, switch on. Look at the light tube itself and other things. So the interesting thing here is that where there is things. The interesting thing here when it comes to these numbers is this number, which is not contamination, but the number of muons that are just going through my detector. And muons themselves are interesting for two things. First of all, the muon itself is not a background, of course. You see it crossing the detector, nothing happens. Muons activate the detector. And muons activating the detector shoot neutrons. And neutrons do things, very nasty things, like, for instance, transform Xenon 136 in Xenon 137, which in turn decay beta, and then it gives you an internal background. So muons are nasty. We want to get rid of them. This is one first look at the different amount of background contributions. And when it comes to background suppression, and we will look at that with a bit more detail in the exercise, basically we have two handles. And one handle is the energy resolution, which in our case, in next 100, we are still assuming 1%, which is what we measure in next white, although our objective is to improve it in next 100 or in upgrades of next 100. And then the topological separation, which in that particular work, in that particular thesis, we knew we could do better than 10%. The recent work that we have shows that we can do, here it was 91% background suppression. Right now we know that we have 95% background suppression. We think we can get to 98, 99% background suppression. But okay, you have these two handles. Now, one interesting thing about the region of interest. In the case of Legend, the region of interest is a very narrow strip, 5 kV or so, because they are in a region flat between peaks. So for them, there is no reason. They just take the region of interest they can take to get their signal, okay? In our case, the region of interest must be asymmetric because you have two peaks together and you need to go right because the bismuth is dropping on you. And this introduces two problems. One, on itself, the background. The guy is trying to rain on you. Second is the exponential nature of the background. So the problem that you have is when you have a background rate, you know that, okay, no matter where I am, it's the same amount of background. When you have something that is dropping because it's a Gaussian, it's an exponential, and you move a little bit left, you have more background than you move a little bit right, and estimating the variations is difficult. Okay? So this is the only way that you have to protect with that is make your resolution as good as possible and go to the shift as possible. Okay? When it comes to background rejection, sorry, this is, oops. When it comes to background rejection, what are our tools? We start, all this, by the way, is Monte Carlo simulations. We don't have the data to back all this thing up yet because the detector, next 100 that I just showed you, went inline a few months ago. Okay, so right now the detector is in what we call the commissioning period, just looking at general data and making the detector alive and understanding what. So anytime in the next few months, we will start to have measurements of topology, of energy resolution, and we will start our physics program. All this is the prediction of what we expect for next. So typically, you start with this amount of thallium, bismuth, muons, and xenon 137. These are the backgrounds. And you keep going on, reducing them. Just the reconstruction, now it comes an interesting thing. Just reconstructing the events in gas implies a huge reduction of the background, but it will cost also price on the signal. Why? Because we are in gas. And in gas, things radiate. For instance, when we produce the 2 electrons that come from the decay of the neutrinoless beta decay, these 2 electrons sometimes will radiate a bremsstrahlung photon. This bremsstrahlung photon goes out of the detector, and then the amount of energy that we measure is out of our window, and this event is lost. And this costs us a relative high efficiency compared with dense calorimeters. But in exchange, it also kills the background from the events from backgrounds. And as a matter of fact, the heat on backgrounds is harder than the heat on signal. Let me give you an example why. Consider the 2.5 MeV region. When I produce 2 electrons for neutrinoless double beta decay, typically, on average, each electron has 1.25 MeV. But when I produce a background from thallium or from bismuth, the electron has 2.5 or 2.6 MeV. Now, an electron of 2.5 MeV bremsstrahlung more, emits more photon of bremsstrahlung than one of 1.25. So when I put a cut saying I want to be inside the window, both the background gets real heat more just by that cut than the signal. Okay? Okay, we just carry on saying, then I want to have a single track. Oops. Oh, sorry. Then I want to have a single track, and the single track thing is very powerful. So you just want to have a single track isolated, reconstructed in the middle of the detector, nothing else. Okay, then you put your Cadena energy on the ROI, and then finally you use your topology. So topology is not the same that single track. Single track says, I will take 1 electron or 2 electrons. And topology says, I want to be sure these are 2 electrons. Okay, so by the end of the day, what we expect to get in next 100, in the first round of next 100, is of the order of 1 count per year in the ROI. This is the first objective, the first goal of the next 100 detector. Now, 1 count per year should be good enough to give us the same rich physics level if we would run sufficient time than other experiments like Gerda or like Cameron Zend. Now, from that one event of background 1.1, most of it is radioactive background, okay? And then the muons in next introduce 0.28 counts. It is interesting that the setup that we have in Canfranc is still completely dominated by the radioactive backgrounds. But as we want to go to a larger detector, we need to think twice what is going on. Let's think a little bit again. Now, extrapolate, right? One background event for 100 kilograms, if we extrapolate if we do nothing else, and we extrapolate to 1 ton, we get 12 events. No, no go. No, cannot. No do. Okay? Which implies that to go to the next, to the ton scale, to build the ton scale thing, from the projection that we have today, which we still need to demonstrate, we need to go down an order of magnitude. So this is the eternal problem of neutrino-less beta decay. How do we want to do that? So the first thing that we're going to do is go to the ton scale detector. The first thing we want to do is get rid of the PMTs. We want to get rid of the PMTs for many reasons, including the fact that PMTs will give us background. The sapphire windows will give us background. The sapphire windows will give me problems with pressure. It's a mess. Okay, let's throw them away. But if you throw them away, you need to do something instead. You need to put something. We will discuss what we're going to put in a second. The second thing that we're going to do is a very serious and at the same time very obvious and at the same time very kind of what? Change. Like, oh, what is the big deal? What is the big deal? Muons, no, who gives a damn? Muons comes from everywhere. And why in hell this thing goes to, rather than making, you just keep doing detectors like this and all of a sudden like this? We'll come back to this thing. It's gravity, but gravity in the second derivative of gravity. You'll see. You'll see the second, it's in a second I'll disclose something interesting that has to do with radio purity and gravity. This is why I'm telling you second derivative of gravity. Okay, so the guy is going to be standing, right? Now, dimensions. With dimensions, you can play a little bit. You need to put sufficient volume, right? So on the volume, in our original conceptual design, we had a detector that was a square. That is what I proposed you in the exercise, 2 meters by 2 meters. Currently, we think it's better to have something like a bit less than 2 meters by 1.5 meters. Why? Because we know that we can drift quite a bit. Because the lifetime we are measuring already with next 100, 20 milliseconds. No, 100 milliseconds. It's spectacular. The lifetime is like 100 times the length of the chamber. So we think we can do this very well. And we're going to double the detector. So it's going to become symmetric. And so the thing is we can put 3 meters long and then whatever we need to make it, to hold that on. At 15 bar. Now, I almost squeezed that en passant. The detector becomes symmetric. Why? Well, first of all, because I don't have any longer the PMTs. So if I am claiming that the detector is symmetric, I am either measuring the energy in the planes or somewhere else, yes? Now, give me a reason why I would like to make it symmetric. Why not a symmetric 3 meters? Well, I already tell you one reason. Then I would have to drift 3 meters, which implies higher electric field, implies higher voltages. It's kind of messy. But there is another reason, which is non-trivial, is that if I have a cathode and an anode, this cathode is a 50,000 volts or a 70,000 volts, and I need to let it go to ground. I cannot put a ground plane immediately after 70,000 volts because I have sparks. So I need to give 20 centimeters, okay, 30 centimeters to let this thing go to ground. And this is wasted gas. You don't want to waste gas on this way. So the detector becomes symmetric. Okay. Now, how are we going to measure the energy? You already saw the solution. Legend already gave the solution for us. We're going to make a detector of fibers. And the detector of fibers look in many aspects similar to the shroud of legend. We're not going to go like this. Instead, the detector is going to have fibers that go here or here. The end of the fibers is aluminized. So the light that goes back and comes back. And the fibers go to silicon PMs, and the silicon PMs are put in a ring, and this ring is cool. Why do you want to cool the ring? You cool it from an external fluid because you want the silicon PMs to be cool so that the dark current is small. Why? Of course, in legend they are cool by definition. They are liquid argon. All right. So what we're going to do is to cool the silicon PMs to a convenient temperature so that the dark current does not bother us. All right. And everything that you wanted to know about silicon, about fibers and the fiber optic detector, you can ask Mariam, who happens to be working on this, and her thesis is going to be on this particular thing, and she will tell you everything about detectors and fibers. So I hope that on the Gong show she says something. She said I was going to. Thank you for volunteering. Thank you for volunteering, Marian. They are extremely interested about hearing about the fibers, so thank you very much, volunteer. All right. Now, another thing that we can do, by the way, is to put a little bit of helium on the detector. Why would you like to put helium on the detector? Because this will reduce the transverse diffusion, and that will make our track sharper. Remember that we have all this deconvolution business, right? Well, if you make the less diffusion to start with, you have less deconvolution and the detector is cleaner. So this is a possible trick that we can use. 10% of helium would give us a much reduced diffusion. We could go from 10 millimeters per square root of meter to about 2. So this is a trick that we want to consider. And now this is the kind of things that you do with a Monte Carlo to write a paper and to show the funding agencies that you can do it. I'm not going to bother to argue with this. What I'm going to do is telling you what are the problems that we need to solve and how we want to solve these problems. The problem is that for the next step, we are lucky. We don't need to be like 0.1 events of background. Just one event of background per year in the ROI. The same thing that we expect to have in next 100. So how are we going to achieve this factor 10 reduction? So to achieve the factor 10 reduction in reality, what you need, you know that you have, the scaling is already helping you a little bit. Why is it helping you? Because as you double the dimensions of the detector, the surfaces that are your external background, remember, things that shoot you stuff come from the surfaces. So the surface doubles, multiplies by 4, but the volumes multiplies by 9. So you win already by simply doing nothing, keeping the background rate constant, and multiplying your size, you win. Okay? This is one advantage of purely volumetric detectors, that they have something called economy of scale. This is, by the way, the reason why you want to make a nuclear power plant as big as possible. Because the amount of power that you get for the amount of heat that you need to cool it off always improves with size. All right. The second thing that we need to do is to improve the energy resolution and the topological signature, which are our two handles. Now, the topological for both things, we need next 100. To run a Monte Carlo in which I say, okay, since I need to get to one background event, let me put 0.5% energy resolution and let me put this, it's trivial because we can do that in class. you need to show that you can get there. Now, as I explained you in the last class, we have good reasons to think we can make 0.5% because we actually have made this energy resolution in our prototypes. And one of the things we suspect is that the 1% energy resolution that we measure with next white is related with the PMTs themselves. Okay? And removing the PMTs and going to a fiber, barrel fiber, which also has better geometrical properties, should help us to get to 0.5%. So, but now you will tell me, the next 100 is going to operate with PMTs. Yes, on the first phase. So our plan is to run next 100 for the next 2 to 3 years with PMTs and measure the energy resolution. See how it scales compared with next white. And then remove the PMTs, put a optical fiber detector, which we are already starting to build and working with prototypes, and compare. And what we hope is to improve the energy resolution as we should there. So if you guys are interested in working on optical fibers, talk to Mariam. She'll give you some work. So one of the things that we need to do is to improve the energy resolution. If we can improve the energy resolution to say 0.5, 0.6, we will be in much better shape. Because remember, you are moving exponentially away from the background. The second thing we need to do is to optimize at most the topological signature. And there we are quite optimistic because already we see here is technology. We see that neural networks by themselves are doing better than we did by hand. So we are already going from 9%, 8% to 3% or something like that. So this improvement of a factor 3, we think we can get only just because it is possible to train neural networks to see better the topological signature than we had. It is very interesting because this also happens in PET technology. So in PET technology, people used to be not to be able to use monolithic crystals because they could not, with a monolithic crystal, when a gamma arrives, they could not simultaneously determine X, Y, and Z in a big crystal with any classical algorithm. Instead, with a neural network, you can. All right? Also, we expect to put helium, reduce diffusion, so that topological signature gets also better. So, in rough terms, what you need to do to get to reduce the background by a factor 10 is to improve your energy resolution will by your factor 3, your topological signature anything between a factor 3 and 4, and you still need to improve your radio purity. And in order to improve your radio purity, what you need to do is to run your detector and understand what is going wrong. We already got the whole discussion with Ricardo, so I don't need to repeat what we will be doing. Is that understood? Is that clear? So these are the challenges that we have to get to the tone scale. And by the way, we are going to go by steps. So as I said, we will run the next 100 detector for a couple of years, then we will upgrade the next 100 detector to have, so it looks more like Nexton. Then we will put helium and we will go on until we understand how to move on. But now back to my question on gravity. Well, let me finish the presentation and show you. Remember that we discussed this thing with the sail to Ithaca, and the trips to Ithaca always take 20 years. So it is an interesting documentary here. This is a student in 2012. He was just starting his PhD thesis. Now in 2022, the same guy, Francesc Monraval, is the technical coordinator of the experiment. I have, further pictures, 232, we'll keep documenting. So in next, we expect to be the first one to make a docu reality thing where you can see the guy aging until he's 100 years old and show the detector, right? I think that should tell you quite a few things of reality. This is the way we really evolve. we go to bigger and more complex detectors, and we exchange technology by time and effort. All right, before finishing the lessons, a quick go back on the vertical position. Okay, why gravity and second derivative of gravity? Now, copper. This, remember, I need to make ultra pure copper, the plate on the bottom, the plate on the top, and around myself. In vertical position, I need to make bars, and I need to make standing discs. Now, this implies machining the copper. And machining the copper introduces more radioactivity than the copper has. So what I would ideally do is to have unmachined copper, so copper which has been formed in a mold or slightly moved, so it doesn't have any rigidity. So if it doesn't have any rigidity, what I want to do is to just deposit my plate. Now it's not taking pressure. And just deposit rings of copper, letting gravity do the work for me. So because they are standing there, they don't need to sustain gravity. The plate on the bottom is not so much of a big deal because you can put bronze, which is more rigid on the bottom. The plate on the top is something that we will need to think about it because the copper also bends, right? But gravity is helping us to make more radio pure shielding. That's the point. Okay. Because the plane on the bottom is not a problem. We can put bronze on the top. The plane, the staging here, we need to think about because here we will need probably put rigid bars, honeycomb of bars, and the honeycomb bars should be made of something, bronze probably, to keep the thing rigid and not sagging too much. So all what you need to do, so your only problem is on the top plane, which is the one that sags. This part, which is a big thing, they are just rings that come in. They are not taking any structural pressure. The gas and the steel is there, and the plate on the bottom is self-shielded. So the main problem is going to be the plate on the top, which is still something we need to figure out. Okay? All right. This concludes what I wanted to tell you about high pressure xenon detectors. And let me move on to liquid xenon detectors now. Say again? You want to? We'll get there. We will get there. We'll get there. So lecture 6. Lecture 6 is liquid. Yes? Yes. You need to speak louder or I don't hear you. Yeah, radon. Radon. On the cathode, radon and cathode, yeah. So two things. First of all, radon on the gas is not a problem. Radon will, of course, produce bismuth 214 that will drift to the cathode, right? So on the gas itself, you don't care, right? On the cathode, there are two things. We fiducialize the detector. Then anything coming from, it all reduces to amount of bismuth 214 that you have, and the gamma from bismuth 214. Because anything that, any radon product that emanates from the cathode, we see it. And we have a beta region. And the beta region is you cannot be produced near the cathode. So we actually measure, we are measuring this. Actually, I'll tell you what we do these days. In NEXT, what we do is we fill the detector. The first thing we do to commission the detector, and we did that in NEXT White, is to fill the detector with radon. How we do that? Not directly. We just pass the detector, the gas, through something we call cold getters. And the cold getters, they contain a zirconium product that allows a very quick cleaning up of impurities, but they also emanate radon. And so the detector gets all full of radon. Fine. We just look at the radon decays on the 3 alphas channels, and this is the way we use the first characterization of the detector is looking at the alphas and identifying the alpha families. And then we look at the cathode, and we see the huge peak of alphas coming from the cathode, and of course we put a bit and kill all of them. We cut them away. I mean, it's so of course there is something we cannot cut is when there is a fraction of bismuth 214, a very tiny fraction that shoots you gamma. But this is in all other places. So our problem is that the radon contribution is not bigger than the other sources, and this we measure with some detail in next slide, and it was not. So of course we operate in a radon-free atmosphere. The detector itself, air is free of radon, but so far none of our studies show that we need to distillate the xenon, right? So in principle, notice that the ability of vetoing, and this is why, by the way, you need S1. If you don't have S1, and then you don't know where you are in Z. So you could be right on the cathode, and it wouldn't work. So this is the reason why when somebody tells you, but you could make do without S1. No way. The St. TPC in the mid-90s, they were totally dominated by events, radon events coming from the cathode. You are totally dead. Okay? Good. Let's move to the NEXO way. So the idea here, this is an interesting plot. You can make a liquid xenon TPC, of course, and a liquid xenon TPC is essentially the same thing that a high pressure xenon TPC, and nothing changes except that now you are drifting your electrons in liquid. So the amount of, you are having ionization, you are having scintillation, actually more scintillation than in gas. And otherwise, your techniques are very similar, but you have two ways to do this. One is what we call single phase, in which you measure the charge inside the liquid with some sort of charge detector. Okay? And you measure the light, the scintillation in the liquid with some sort of light detectors. The other possibility, this is what EXO did, and this is what NEXO wanted to do. So, phase TPCs. The other thing is the dark matter trick. So here you measure the scintillation light with PMTs up and down, and then you drift, and then you go to a gas phase, and then, like next, you amplify, EL, and then you measure very nicely, then it's just light. Charge converts itself in light, and you measure the energy with photomultipliers, which also measure the position. Now, as I was, our original idea for NEXT was all this gas and PMTs actually. Okay. Now, of course, I gave you a lot of, I have been complaining for a while about PMTs. Why the dark matter experiments can afford PMTs? Okay. For two reasons. First of all, because they are not under pressure. PMTs can operate without a problem inside the liquid. They don't need to be decoupled from the liquid. Second, because it's not that they have so many options, because they cannot use TPV. Therefore, they need VUV sensitive photomultipliers. Third, because although it is true that the photomultipliers are somewhat radioactive, they are gonna look into the central part of the detector and self-shield themselves from the radioactivity of the PMTs. Okay? Fourth, because the main goal of dark matter has always been lower energy. Lower energy is even more shielded than high energy gammas. So this thing would work, but you also should ask yourself the question, okay, if it works for dark matter, maybe it also works for neutrinoless beta decay. We'll come back to this question later. For the time being, I need you to understand that these are two different techniques. And now, a question, which one of the two has better energy resolution? Silence. You should know. I have already explained you enough for you to know. Which one has a amplification? In single phase, can you amplify the charge? Can you amplify the charge, yes or no? No. Why? Avalanche multiplication. So you're going to read without amplification. Fine. No fluctuations, but little measurement, small. In two-phase, you are like in X, linear amplification. So you can get a lot of light with only sub-Poissonian intrinsic fluctuations. Good resolution. So which one of the two has better resolution? Okay? So this is something important, and this is something that is kind of curious because we'll come back to it has consequences, as we will discuss soon. But it should be obvious for you that this one has better energy resolution because of the amplification of the charge. By the way, both of them need to do the same. They cannot read only charge or only scintillation. They have to anticorrelate them. Okay? If I do what? Then the fluctuation is going to kill you. I mean, your problem here is as soon as you put a fluctuation source that is dominating, it's dominating. So in the case of, we did the trick, for instance, with non-amplification, putting micromegas in X at the beginning of our R&D. And the gain fluctuations were of the order of 3%, 4%. So if you don't amplify, you don't have the problem, but then you have less charge. And then you have also fluctuation because you have a number n of charges, which is smaller. All right. Now, single phase TPC, this is the Nexo proposal. And the idea is, look, the charge is there is a bit more of charge than in the case of gas. The idea is the same. Now here, notice that this is an asymmetric TPC. Now, let me, I already told you some stuff. Does it make you happy, this asymmetric TPC thing, for them? No? If it is an asymmetric TPC, and this is about 1 meter, they need to drift, they're going to put a cathode, they need to leave some space here. So this is wasted. And now, you could tell me maybe it's not that much. But actually, as you will be able to do when you complete the calculation, so Nexo is claimed to have 5 tons of liquid xenon. 1 ton already goes into dead spaces. Okay? So when you have liquid, anything that is not full, that is not active, is a tremendous waste because liquid is more dense than gas. So if I have 10 centimeters of cathode degradation in gas, is way less mass than if I have 10 centimeters of cathode degradation in liquid. But otherwise, the TPC is the same ideas that we already know. We have already discussed that. Now, the other question I wanted to ask you is why, but I already gave you the solution, but please tell me why we could put fibers, you know, why the light, the scintillation light with fibers in Nexo rather than with another complicated system that I will describe? Why not? This is a test that to learn if you were, awake or sleeping. And the answer is that you were sleeping. Attacks TPV, not fibers. Fibers, liquid xenon, and fibers work just fine in liquid argon. But liquid xenon, damn it, attacks TPV. And then you cannot put TPV, and then you cannot shift the light of 172 nanometers to something blue. All right? So you cannot use it unless you invent something that is not attacked by liquid xenon. Liquid argon does not attack TPV. Damn it. Okay? Fine. So now what is the reason why liquid xenon is a good idea? This, and why you need a big detector. A gamma of 2.5 MeV has attenuation length of 8.7 centimeters, almost 9 centimeters. So if you make a small detector, then okay, you don't attenuate anything. If you had a detector like EXO 200, you don't attenuate that much either, right? Because the gamma penetrates. But if you have a big enough detector like EXO, then you attenuate a lot. And this attenuation kills most of the backgrounds that come from outside, and it's extremely effective. Okay? So Nexo wants to approach itself to this perfect shielding detector. The way I get rid of my backgrounds is by killing them before they arrive to my region of interest. End of the story. Okay? Now, go ahead. Yes, I was in the problem that I put you yesterday. So if you would have not run away at 4 a.m. when I went for a coffee, you would have solved it and that question would not be asked. Correct. So here it comes the deal, and we will discuss that in a second. I am going to have my detector. I am going to have my fiducial volume. And my fiducial volume should be scaled up to my, actually, this is something that you could do by hand, compute how much attenuation. The only problem is how much you pay. And actually, we know how much, because Nexo tells us, is because we can do the calculation. If you do the calculation and say, okay, well, and I want to attenuate enough, I should stick to 1 ton internal volume. Now, 1 ton internal volume is a lot of mass and is very well shielded, but you have put 5 tons. So you start your thing by paying straight away 80% of your hyper expensive xenon, you give it to the gods. So it's like a sacrifice. You offer a sacrifice of 80% of your troops to the gods. Shit. All right, but this is the way it is. Now, there is a better way. I invented it actually. Just make the ton of enriched xenon and the rest of normal xenon. Right? The only problem is that they will want to mix, no? Oh, well, let's separate it with a membrane. And this membrane has to be zero background and totally transparent to charge and to light. Easy. Make it of graphene. So you guys should quit. Don't do anything more. Go and make solid state physics. Learn how to make a balloon of pure graphene, and then come back and win a Nobel Prize. Okay? This is a paper we published. Please look at it. It's called GRACE. And we did it with graphene theorists that show that graphene has magical properties. It introduces basically no background because it's 1 layer of atoms. And it's transparent to ultraviolet light. It is really beautiful. The only problem with graphene is that you need to make that big balloon, of course. And for the graphene theorists, it was very easy. But I haven't yet talked to graphene experimentalists that find it very easy. All right. About graphene balloons? Okay. So you want to have argon, maybe, argon and then xenon. So two things, argon and xenon freeze at different temperatures. So it's a bit of a problem, right? So that already would prevent you to do anything serious. So since you want to have to be liquid at the same temperature, by the time you are liquefying argon, you are solidifying xenon. So maybe you could have a block of solid xenon. Good idea, try it. Maybe we could have a block of solid xenon like a brick, right? Frozen by argon. Why not? Why not? Maybe it works. Notice that we will need to separate one thing from the other. And this implies a physical separation. And notice that you need to let the light go out. So how do you prepare a membrane? Because you will see when we see Kamlan's end that you can do that. But you can do that with normal light. With 172 nanometers light, I know of no membrane except of graphene that lets the light go out. So difficult. Okay, graphene is the solution. Okay, guys, let's carry on. Anticorrelation is needed to get the energy resolution. This we already understand. But this is what EXO measure. So EXO measure 1.15% energy resolution, sigma. Now multiply by 2.35 and you get 3.5%, which is not bad, but not good either. 3.5% will kill many backgrounds, but the bismuth gamma will be all of it there. So this is a problem. Well, this is a problem. This is an issue. This is a feature. Can you improve in Nexo? Yes. It's a better detector. You can collect more light. You can do that. How much can you improve? You would like to know before you build the detector, but you cannot actually. But I give you a few clues. Anyway. The other thing that you would do with Nexo is topology. This is you already heard from Ricardo's talk. If you have a Compton, you will have double sides very often, and then you get rid of that. In liquid xenon, it's even better, because liquid xenon is less dense, so things fly more. So anything that flies more than about 3 millimeters, you will see able to see. This is extremely strong rejection, except that the photoelectric bismuth 214 gamma is photoelectric, nothing to reject. Okay? So these are the three handles that you have in liquid xenon. Energy resolution, as we have seen, not that efficient, at least for one source of background, bismuth 214 gamma. Topology, very efficient for almost everything, but not for 214 gamma. And then standoff, very effective for everything, including 214 gamma. Okay? Now, this is the EXO detector, which ran a few years ago. Notice how small the thing is. It was like this. Okay? How did EXO work? They measure the charge with wires. They measure the light with APDs. Okay? Avalanche photomultiplier detectors, which work very well in liquid xenon. And so they got this very pretty detector, very small. What was the problem of EXO 200? They got good energy resolution, but not super terrific, because they didn't have an excellent light collection. All right? And they got shielding, but not super terrific, because it was a small detector. In spite of which, the guys, so this is what I was discussing a second ago. You see Legend with all these shiny, sharp peaks. Then next, where the peaks are still very clean peaks. In EXO 200, the peaks are already not so clear peaks. Right? Anyway, here's the thing. The Nexo, when Nexo ran, they got a background rate, which was, they got a few events. Actually, in the extended row, they have quite a bit, but when they went to the final number of events in the small ROI, they had quite a few, which reduced to about 1 event per background in the ROI. So basically, what they got out of this was, okay, I have a good sensitivity, the number of background events I will need to reduce by a factor 20, and I have measured this energy resolution. So I am going to scale things up. And now scaling things up in liquid is extremely effective because, again, you're winning with an exponential because the gamma is exponentially being attenuated. So let's make this thing big, 1.2 meters by 1.2 meters. Then, of course, let me put this thing into a matryoshka thing. So I put this thing inside my cryostat, inside double shell cryostat, inside my water tank detector. And the no, the shells are I just got it's something way cleaner than it was some kind of carbon fiber, but now they have changed to something else. I'll tell you later because I got an email from Andrea Pocar, extremely clean things. So the double shell from the cryostat, I don't think will give them any background at all. And they want to stay in a snow lab, which is very deep and within water, so they are also in very good shape if they overoperate there for neutrons, for internal backgrounds. Then the tiny TPC here in the middle, made of copper, and then they're going to read the charge with a tile. So the thing will be made of quartz, okay? So rather than cross wires, it will be like strips that cross, and this strip will be etched in quartz. So it's basically cross wires in modern way. And then they will read, by the way, technologically, everything is very challenging because the wires, your problem is not only to read the charge in the wire, where do you put the electronics, right? So they're going to put an ASIC on top of every pair of cross wires. So the electronics have to be radio pure also, and it has to work in cold. Challenging in both things. Now, this is the copper, and the barrel, the way they're going to measure the energy is basically with a wall of silicon PMs. Again, with the electronics on top. Okay? So, what is the takeaway message? The takeaway message is that this one. When you are working with high pressure xenon detectors, you don't have effective self-shielding. Gammas will interact in your detector, and then you have these two handles, energy resolution and topology. When you're working with liquid xenon detector, you have energy resolution, but not so good. You have topology, but topology does not have 2 electron to 1 electron separation, but you have a standoff, you have self-shielding. Okay? And these are the two different approaches that you can use with the same kind of technology, TPC. A last word before we move on. The last word is as follows. Could you do the same thing, but rather than using 5-ton detector, now you say, okay, next generation dark matter detectors. They are talking about 60 tons of xenon, maybe 80 tons of xenon. Suppose there is 60 tons of xenon. The detector will be 3 meters by 3 meters, maybe, something like that, maybe 4 meters by 4 meters. 60 tons of xenon, normal xenon, will contain 6 tons of enriched xenon, of xenon 136, distributed over all the volume. You now can make an inner volume of order 10 tons in your 60 tons, which contains a ton of xenon. And can you do for free the neutrino beta decay experiment? Well, the dark matter people claim yes. The EXO people claim, we can do better. I'll give you one argument to each side. In favor of dark matter sort of experiments, they have better energy resolution, for sure. They have actually already measured 0.7% sigma. And so they can for sure get to 0.7% sigma, while the target of Nexo is 1% sigma. So energy resolution like the guys on dark matter are better. Counter argument, fragment in inner backgrounds, internal backgrounds. Internal backgrounds, now you have to live with 60 tons of xenon. That will give you way more xenon 137 than with 5 tons of xenon. So it depends on your persuasion, okay? But it is important to realize that it can be done eventually by these dark matter experiments. So this concludes liquid xenon and the session of the morning too. Go ahead. In what, in dark matter? Oh, you will have shielding, same thing. Mm-hmm. No, and then you make your detector is way bigger now. So now you count your 60 tons by about the same distance. Now you don't have 1 ton, you have about 7 tons. The total amount of xenon that comes in your detector is depending on how much money they have, but let's call it 60 tons, 10 times more. Out of which your xenon of is dispersed. Your self-shield is the same. I mean, xenon, no matter whether it's enriched or not, they know it's the same thing, right? So it is this kind of simple thing. Rather than something like this, you scale things up. So here you have 1 ton, here you have 10 tons, and the attenuation distance is the same. Right? Now in 10 tons you only have 1 ton of good xenon, but it's the same. So the scaling up plays in your favor. Overall, I have the same amount of useful xenon because I start with 10 times more, and for the same amount of shielding, but I have better energy resolution. And then the only thing is, okay, you have better energy resolution, but you also have more xenon 137. If you do the calculation, the dark matter people are convinced they can do it. Of course, they have one advantage. Both of them are for the time being projects, right? But the advantage of the dark matter, obviously claimed by the dark matter people, is that they would kill 2 birds with the same rock, right? All right, liquid xenon is done. At what time we have the break? Now, no? Oh, okay, perfect. Perfect, because this is exactly what I need to give you to finish the lecture. So, last lecture, I don't know if you ever heard, you're too young also, but there was a very famous book that some of my generation read, which was called Zen and the Art of Motorcycle Riding. That was a beautiful book from the gypsy times, from the hippie times, which I recommend you guys to read. It really describes the feeling of a time. So I have decided to call this lecture Zen and the Art of Neutrinoless Beta decay searches with Kamlan Zen, of course. Now, Kamlan Zen, it's a little bit in the direction of what you wanted to do, but it's slightly different, right? So now, again, I want to do self-shielding. I happen to have, of course, the idea is not, doesn't come out of thin air. Kamlan was a very successful liquid scintillating detector that did look at the nuclear reactors all around themselves and help to establish the neutrino oscillation. An extremely beautiful detector. And in ChemLens, you have all these amounts, kiloton of liquid xenon. Liquid scintillator already very radio pure, very well understood. It's not that you build such kind of detector in one day. It's that you happen to have this detector and you have been operating this detector for 20 years, so you have the machine ready. Now, the brilliant idea that Inoue-san had was, okay, let me make a balloon, okay, and this balloon I will fill with liquid scintillator again, but I will dissolve the xenon in my liquid scintillator, okay? I can solve xenon at about a fraction of a couple of percent in liquid scintillator, so whatever I put, maybe 20 tons of liquid scintillator here, I want to put like 1 ton of xenon. So 1 ton, I will put enough liquid scintillator here to keep 1 ton of xenon here inside. My balloon will be made of extra super duper radioactive thin clean hell acrylic, and this thing is transparent to the blue light, not to the VUV light. But what happens with xenon when xenon scintillates in liquid scintillator, because it's very hard, the radiation, what do you expect these gammas to do? These hard VUV gammas will excite the liquid scintillator, which will shine again in a proportional way and produce blue light. So you transfer the VUV light of the xenon to the blue light of the liquid scintillator. So now you have signals on blue, and then you surround with PMTs. So this is a spheric detector with PMTs all over the place. The photomultiplier background is totally shielded by the external liquid scintillator. I only need to worry about the background coming from my thin balloon and, of course, internal backgrounds. And if you look at the thing as it is, first of all, you can see the advantages. Advantages is that I can put a lot of xenon straight away. Second, the thing is going to be very well shielded, okay? So it gives me an edge. It gives me the possibility of starting a big experiment with a lot of mass while the other guys are still, playing with grams. You just go to tons. So this is what exactly the ChemLens decided to do. Now, disadvantages. First of all, here, unlike all the TPCs that we have seen, you don't have position. Oh, you have position. You see all the PMT shining, and then you say, it's here. So you know whether you are inside your balloon, for sure, with good resolution, but good resolution is not millimeters. So you now don't have the separation between different fragments. You're going to eat all the Compton. Worst of that, when you have fragmentation products of xenon, most of the time when I activate xenon and I make xenon something, xenon will decay, and most of the times I will see just a mess of constellation. But if xenon decays now all together, I will eat it, okay? Because I don't have cluster separation. Okay, they have many other tools though, but let's get the clarity. The other problem is that the energy resolution is dominated by photon statistics. So the current ChemLens has a sigma resolution, full width maximum resolution of 10%. And 10% is not good enough even to get out of the 2 neutrino mode. But you can improve on that. But you are limited by the fact that now you have a very big volume, right? And light gets lost. So let's carry on with the detector itself. So this is the way, so they make the nylon balloon, they put the detector, and by the way, they put a few hundred kilograms. Already 7 or 8 years ago, they were the first one. So EXO had kind of got to 10 to the 25. So the first day they switched the detector on, they were at 10 to the 26. So, everybody was like, come and say, blah, 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 and then they saw the result. The guys are good. Okay. Then currently, they have almost 800 kilograms inside, and they are running the show. Their last number is few times 10 to the 26. So they have the best sensitivity in the market. Okay? And then they want to go in the future to a much better detector, Kamlansen 2, to get to 10 to the 27. Now, balloon. The balloon is just a beauty. You need to be Japanese to do that. Otherwise, unless you are Japanese, forget it. You will not do it. It is done with the same refinement you would do the tea ceremony. The whole monster balloon weighs a few kilograms. It's made of micro thin. It is held out by, the whole preparation thing is like space kind of thing like. They've been working on that for years. Okay, at the beginning of the run, they found they had a silver contamination. The silver contamination came because some of the components of the strings that hold the balloon came from a region where they had got some fallout from Fukushima, whatever. They have been working forever. Bottom line, they have really very low background here. What is this? Scan completed. Shit. You cannot stop. Okay. Now, of course, when I am inside my balloon, we are in the same situation, more or less, than EXO or NEXO. If I go to the region where I have the balloon, which is here, you can see it, right? I have a big concentration of background. You can see it, right? So I can always get to a very, very clean region, going lower in radius, here, for instance, right? So you have all this high background region, then you have your balloon, and then you go to the clean region. But of course, as you go to lower and lower radius, you pay Xenon on it. So the cell shielding is more or less the same thing that we had in Xenon, but now my Xenon is diluted. So the liquid scintillator is helping me to shield. Okay? So in that sense, I am paying less. Now the other thing is, look at the this is done in gram programs, which the translation to, you need to do the hand calculation, but it's extremely low background. 10 to the minus 12 gram per gram is really extremely low background. So, what? Now, of course, the other imbecile. So here is the problem. The problem is that you have xenon, and eventually you get neutrons coming in, and the neutrons will make xenon spallation, and all the xenon spallation products will try to fake your signal. Some of the spallation are short. You can tag them. You can get rid of them. Some of them are long, and it's hard to get rid of them. Now, here is a picture of the situation for them. This is the ROI, where they search a signal, and these are the background things. Notice they have the two neutrino component, it's here. So they have a little bit of neutrinos. The 214 bismuth, our old friend, is here. So they get all of them because they don't have the resolution. Then the thallium is also there. They get all of them because they don't have the energy resolution. So when they do their sophisticated analysis and they end up with the kind of things they get, they end up with a total number of expected events, which is of the order, it's not written here or somewhere, but it's the order they expect like 7 or 8 events, okay? Exactly like 8 events, and they find 8 events and they subtract it, and they get a very good limit. Actually, the best limit in the market, order 4 times 10 to the 26. Now, I told you many times, we have insisted, all of us, that your experiment for the future needs to be zero background. How come that these guys can live by background and subtract it? The reason is that they are playing, remember the formula that I showed you the first time? In the denominator, you have C over delta E. In the denominator, you have exposure. So when we say tone scale detectors, typically we say tone scale detectors of very low background. So all my mass is useful. But what Kamlansen does is a trick. It says, okay, my C over E, C is very tiny because they have all this self-shielding. Delta E is large, but I compensate delta E with MT. So typically, Kamlansen operates in the regime, gets, put it that way, Gerda has got 10 to the 26 effective limit, a little bit more than that, with an effective mass which is not quite 100 kilos, no? 40 kilos, okay? Then Kamlansen gets to about the same sensitivity with an effective mass which is 800 kilos. So what they say is the brutal approach. Okay, fine. I have backgrounds. Okay, I'll subtract them, right? Because I trade mass by. So the problem, you could always do that, by the way. The problem is that trading off becomes harder because of the square root of the subtraction. All right? And so this is the reason why Kamlansen, when they want to go to the second phase, they say, okay, the trick of Kamlansen, which has worked so far, to get me to the 10, repeat, Gerda is like 2 times 10 to the 26, they are like 4 times 10 to the 26, like, oh, I'm the best guy around. But in practice, the same level of sensitivity has been made trading of mass by energy resolution. I cannot carry on doing that to the next level because I have a square root that kills me, yes? So they plan for Kamlansen 2 is to improve the energy resolution. And for that, they use all kinds of tricks, including Whiston cones, that would allow them to concentrate the light. So what they want to do is to get from 10% to 5% or better energy resolution. Now, of course, as soon as you reduce your energy resolution window, you get rid of the 2 neutrinos. The second thing they are going to do, which is incredibly beautiful, is there. They're going to do a scintillation balloon made of pen film. What is this? The balloon, every time that, remember the bismuth 214? When you have bismuth 214, there is one alpha always there. So the gamma goes, but there is one alpha. The alpha will excite the pen, and it will shine. So by scintillation, they say, oh, this guy. So they have another trick, incredibly pretty trick, okay, to reduce the bismuth 214 thallium 228 background. So the combination of reducing background by energy resolution and by further tagging allows them to think they can get to 10 to the 27, not because they increase the mass, but because with the given mass they already have, they now go to the process of background reduction. Okay? So this is the third technique that you can use in Xenon. And my personal take is that the 3 techniques can get to 10 to the 27 sooner or later. In anything that is half to 1 trip to Ithaca, so half to 1 unit, you can get to 10 to the 27. As I hope I don't need to repeat, because I think Ricardo has made abundantly clear, 10 to the 28 is a completely different game, because you have gone through all the pains in hell to get to the regime of about 1 background event per per interROI. And now you need to go to 0.1 background event. It's hell. So what we will do this afternoon we will do two things. We will review first, quickly, the problem, the exercise that I put you yesterday. I will show you where my notebooks are, so that if you are curious, you can look at the thing. And then we will describe a possibility to go for ultra-low background experiment, what we call barium tagging. Now, barium tagging today is just an R&D, it's just a long-term project, but this kind of long-term projects may be the only way out for the field. This is an important notion, and this is the reason why I want to do it in the blackboard and not showing you propaganda transparencies. I just want to go to the concepts, okay? Why this kind of R&D is important? To repeat, because Legend will get to 10 to the 27 in a few years before than everything else, for sure. Cupid will get to 10 to the 27 with some pain, but they will get there. And some Xenon experiments, or more than one Xenon experiment, will get to 10 to the 27. So you give me 10, 15 years, the field will have explored that region, and either we'll make a discovery, which will be confirmed by several sources, or we will all agree that there's nothing there. Then when you want to push further, conventional techniques may work, Legend may work as well, but I hope that Ricardo has convinced you it will be hell. So we really need to think out of the box and try to see if there are sufficiently crazy ideas to guarantee that we have zero background. So this afternoon we will see one of those sufficiently crazy ideas. Meanwhile, let's have a lunch.